SwayamPrabha. Digital India. Educated India.
Very good afternoon. I welcome you all to the session of Thermal Engineering Basic and Applied, and today we shall discuss about gas turbine units, and to analyze the performance of gas turbine units we shall discuss about another thermodynamic cycle, and that is the Brayton cycle. In the last a few classes, in particular during our discussion of steam power module, we have discussed about the vapor power cycle, and the sole purpose was essentially to produce power. Now, for the gas turbine units again we need to discuss about gas power cycle, and the objective is to produce power, but if you try to understand vapor power cycle and gas power cycle, only the difference is the working fluid. In a vapor power cycle we have discussed about the power generation, power production using a working fluid, that is steam or steam water mixture, but here for the gas turbine units power will be produced through several processes, and those processes will be executed in several units, and the working fluid is gas. So, for the gas power cycle, Brayton cycle is the air standard cycle. I would like to discuss again that whether we have discussed about steam power cycle or we have discussed about the gas power cycle like Otto cycle, diesel cycle. In all those cycles essentially we had to map or compare the processes with an air standard cycle. For example, for the gas power cycle that we have discussed about the Otto cycle, diesel cycle. So, basically that air standard cycles, those are used to analyze the performance of a petrol engine or a diesel engine or the Otto cycle and diesel cycle. But for the vapor power cycle, that it is not the gas, rather it is a pure substance. So, we had to analyze the performance of a steam power plant using another thermodynamic cycle, that is the Rankine cycle. So, today we shall discuss about gas turbine units, and let us start our discussion with the classification of the gas turbine units. So, gas turbine unit there are two broad classes of gas turbine unit. First one is open cycle gas turbine unit, and second category is closed cycle gas turbine unit. So, these two are the two different classifications of the gas turbine units. Now, we shall be discussing about both open cycle and closed cycle units with schematic depiction. I would like to mention here, like Otto cycle is used to compare the performance of a petrol engine, diesel cycle is used to compare the performance of a diesel engine, Rankine cycle or modified Rankine cycle is used to compare the performance of a steam power plant. Similarly, open cycle gas turbine unit, to be precise, the air standard cycle, Breton cycle. So, this air standard cycle is used to measure or compare the performance of the gas turbine units. So, what are the applications of these gas turbine units? Applications are aircraft field, propulsions and also captive power plant. Typically, you know that for a gas cooled nuclear reactor, a small gas turbine unit is used. Open cycle gas turbine units are used mostly in aircraft field and propulsions. So, I am writing here used in aircraft field or propulsion, and closed cycle gas turbine unit is typically used in captive power plant. In particular, in a gas cooled nuclear reactor. Basically, you know that energy which is produced due to nuclear fission reaction, that energy is absorbed or taken by the gas, and that gas is again allowed to expand in a turbine, and we try to obtain work output. So, now let us discuss about the open cycle gas turbine unit through schematic depiction. So, this is the compressor, air is drawn into the compressor, and when air is passing through the compressor, you know that compressor is used to increase the pressure. So, essentially air will be compressed and pressure will be increased, temperature also will increase, but the most important part is to increase the pressure of the working fluid. So, air is taken from the ambience, and that compressed air is now taken into this combustion chamber. Wherein fuel is sprayed, fuel supply, and so basically compressed air is allowed to pass through the combustion chamber, wherein fuel is sprayed and combustion will occur. It is because of this combustion, combustion reaction to be precise, the pressure of this working fluid will increase further, temperature of the working fluid will increase further. So, essentially the working fluid that comes out from this combustion chamber is now taken into this turbine, and finally, so this is state point 3 and this is state point 4 and this is the turbine, and we will be getting W work output. So, basically try to understand, ambient air will be taken into this compressor, air will be compressed, and at the exit of the compressor air is having high pressure, temperature is also higher than its temperature, higher than its inlet temperature of course. That air will be now taken into this combustion chamber wherein fuel will be sprayed. It is because of this combustion reaction, temperature and pressure will be increased further of the working fluid, and that working fluid is further taken into this turbine wherein the working fluid is allowed to expand and we obtain work output. Now, question is, to run this compressor we need to feed some amount of energy in the form of work. What is done essentially so basically this, what is done, this compressor shaft is connected to the shaft of this turbine, right. So, basically what is done here, so compressor shaft is connected to the shaft of this turbine. When turbine is producing work, I should say a significant part of that output work would be absorbed by this compressor for its operation. Now, essentially the work that will be getting from the turbine, that is W net equal to W turbine minus W compressor. So, turbine work that would be available at this shaft, at the shaft of this turbine is W T minus W C. So, this is basically turbine work and W C is the compressor work. So, this compressor work is input and turbine work is output. So, had we not connected this shaft of this compressor with this shaft of the turbine, we could have obtained turbine work, that is WT, but what we can see from this schematic depiction is that a significant part of this turbine work will be absorbed by the compressor for its operation. Hence, we will be getting net work output, and that is WT minus WC, and WC is basically the amount of work that we need to feed to this compressor. So, this is basically open cycle. Now, why it is open cycle, you try to understand, we are taking the working fluid from the ambience and finally the working fluid is again discharged into the ambience at at the exit of the turbine. So, this is discharge to ambience. Okay. So, this is called open cycle because working fluid is not further taken back to this compressor. Had we tried to recycle back this discharge, that is the working fluid that comes out from the turbine into this compressor, then the cycle would be the closed cycle gas turbine unit. So, not only this, there are a few aspects that we shall be discussing in the context of closed cycle gas turbine unit, but this is the case. I would like to tell you a few important points pertaining to this unit, that is open cycle gas turbine unit. See, in the combustion chamber in real case high pressure and temperature is also high, air will be supplied into this combustion chamber and then fuel will be sprayed therein. So, combustion reaction will occur. Now, when combustion reaction will will occur or combustion will occur, we will be getting products of combustion, and the products of combustion are certainly different from the reactants. Now, the effect being a gradual decrease in the chemical energy of the fuel when you are supplying fuel. So, basically the fuel is having chemical energy. So, the effect is being, if we allow not to have any heat transfer from the combustion chamber into the surroundings, then the sole effect would be a gradual decrease in the chemical energy of the fuel and simultaneous increase of the enthalpy of the working fluid. So, in real case it is because of this combustion with a reduction of the chemical energy of the fuel, enthalpy of the working fluid will be increased. But to simplify the entire combustion process that would be used to quantify the mathematical form of the efficiency of the gas turbine cycle, it is assumed that equivalent amount of energy in the form of heat that would be generated because of this combustion will be now transferred to the working fluid, and that energy as if is coming out or being liberated by the combustion reaction. So, this is basically the important thing. Another important thing is that the closed cycle gas turbine units cannot be compared with the constant pressure cycle, because try to understand here we are again further discharging the working fluid to the ambience. So, it is not a constant pressure cycle. Second thing, when we would like to map the processes, what are those processes? Compression of the air, then combustion, that is basically equivalent amount of heat addition, and finally expansion of the working fluid in the turbine. So, the combustion process, as I said few minutes back, can be mimicked by an equivalent amount of heat addition to the working fluid at a constant pressure. The question is, here the working fluid is air or gas. Now, the specific heat of the gas will vary because it is function of temperature as well. So, we have to assume that when the working fluid is getting compressed in a compressor or it is getting expanded in a turbine, we can certainly consider an average value of Cp and also gamma to measure the performance or to measure the processes those are there in a compressor or turbine. Another thing is, in an open cycle gas turbine unit, if we try to now map the processes in PV diagram, so what we can see, compression process, that 1 to 2, that process can be mimicked by an isentropic process, that is reversible adiabatic process. It is very difficult to achieve that process in real applications, but we can assume that the process is reversible adiabatic isentropic process, and that process is represented in this PV plane by this 1 to 2, that is PV power gamma is equal to constant if we try to analyze the performance using different air standard equation. So, now then process 2 to 3, that is at constant pressure heat addition, and finally, so this is 4, that is the expansion process. So, basically 1 to 2 reversible adiabatic compression, 2 to 3 constant pressure heat addition, that is essentially mimics the combustion process, and 3 to 4 reversible adiabatic expansion. So, all these processes, but see now this is an open cycle. So, we did not connect the state point 4 and 1, though condition of the working fluid at state point 1 is the ambient air, and when the working fluid comes out from the turbine, it is discharged into the ambience. So, the state point would be ambient condition. Now, temperature will certainly be higher than the ambient air, but we are directly discharging into the ambience. So, this is the open cycle. Now, question is, as I said that open cycle gas turbine units are used in most of the aircraft, in mostly in the aircraft fields. One important drawback is air is directly taken from the ambience. So, that air will be now allowed to pass through compressor, then turbine. Air that will be drawn into the compressor from the ambience, it is very likely that foreign particles will also enter with the air stream, and those foreign particles will now will interact with the turbine blades as well as compressor rotor of the compressor. So, what will happen that those particles may create problematic issues essentially for the turbine blades and also the compressor rotor. What is done? So, we need to ensure that air that should be drawn into the compressor should be properly screened to eliminate those foreign particles. So, high quality filters are needed, but if we somehow can recycle back the air that comes out or gas that comes out from the turbine into the compressor again, certainly we have to release certain amount of it. As I said you, the state point 4, though it is directly that gas or air is discharged to this ambience, but that state point 4 is not exactly equal to state point 4 thermodynamically. Certainly pressure and temperature of the working fluid at state point 4 is higher than the state point 1. So, next is that if we try to reuse the gas that comes out from the turbine, that means if you like to recycle back that working fluid, perhaps that contamination due to foreign particle of the incoming air stream can be avoided or can be prevented. So, now we shall be discussing about closed cycle gas turbine unit. See, basically we need to close this. So, the gas that comes out from the turbine will be recycled back to the compressor through certain process. So, if we try to draw the schematic, now So, this is the schematic depiction of a gas closed cycle gas turbine unit. So, this is the turbine, this is basically heat exchanger, this is also a heat exchanger, and this is the compressor. So, you can see again the compressor will be, the shaft of this compressor is connected to the shaft of this turbine. A significant part of this turbine work output will be utilized to run this compressor. Here it is not the combustion chamber, rather it is a heat exchanger. So, the working fluid in this circuit, now in this heat exchanger, few minutes back I said that the closed cycle gas turbine units are used in captive power plant or in a gas cooled nuclear reactor. So, what will happen if I try to draw here, maybe there will be another circuit through which high temperature working fluid stream will be allowed to pass, and in the primary circuit the working fluid will absorb that heat, and that upon receiving that heat or energy to be precise, working fluid temperature pressure will increase. Essentially we are trying to mimic the entire combustion process by this heat exchanger unit, and the remaining process is similar, then the working fluid will enter into this turbine and again it will expand, then W net will be produced, that is W turbine minus W compressor, and here we need to reject certain amount of heat. So, this is Q out, and here as if we are supplying certain amount of Q in. So, upon receiving this amount of energy in the form of heat, the working fluid in the primary circuit will be having I mean the thermodynamic state of the working fluid will change, and then at state point 3 the working fluid will be having high pressure temperature, it will expand in the turbine, and instead of directly discharging the working fluid into the ambience, now what is done here, that working fluid is again taken through another heat exchanger, wherein that working fluid releases certain amount of energy to another stream, and then that stream is again further, that working fluid is again further taken to this compressor and cycle is getting completed. So, this is basically closed cycle gas turbine unit. Now, question is, also I could have discussed another important aspect which is valid for both closed cycle and as well as open cycle. What do you expect, that if WC is a significant part of this WT, then certainly efficiency of the plant will be less, rather very less. So, this is one of the one important factor. Second thing is that though we could map or we will map the processes by an reversible adiabatic process. What are those processes? Compression process and the expansion process in the turbine, expansion of the gas in the turbine. So, in real case these two processes will certainly have high degree of irreversibility, and accounting for that irreversibility, actual efficiency of the turbine unit will certainly be less. So, that means the work output that we are expecting for a given design condition, the actual work output by the turbine should be very much less than the rather this WT, that is what I have written here, that is we are assuming that this work will be produced if we consider the process to be an isentropic process, reversible adiabatic. But as I said, in real case this process will encounter high degree of irreversibility, and accounting for that this Wt should be even less than the predicted value by using this isentropic process. Similarly, here I had written that Wc is the work input to this compressor, right. Now, if this is the amount of work needed by assuming the process is reversible adiabatic in the compressor, so then the actual work that we need to supply to the compressor accounting for the irreversible losses should be more than this. So, essentially what we can understand, the W net will be reduced. So, Wt should be even less, Wc will be more, and the gross effect would be reduction in W net, and W net becomes so less that self sustaining of this unit becomes an problematic issue. So, while we will be considering the process either in a compressor or in this turbine, we have to assume that process or processes are not reversible adiabatic. So, now let us discuss about the when compression process and expansion process in the compressor and in the turbine is are not reversible adiabatic. Processes. So, now let us try to discuss about this particular aspect here now. So, what we can do, we can again map the processes in another plane, that is Ts plane, and we also can map the processes in PV plane. As I said, for the open cycle gas turbine unit, so this is 3, this is 2, this is 1, this is 4. So, this 4 to 1, that process is a new process for this closed cycle gas turbine unit, because if we try to recall the PV diagram for the open cycle gas turbine unit, we can see that these 2 points are not connected because there is no process. But now we are having another process that is represented in PV or Ts plane by a constant pressure heat rejection. This is a constant pressure heat addition, not only at constant pressure. In reality, in real application, that when there is basically combustion will be there, and it is because of this combustion we are trying to discuss here using a simplified schematic diagram. So, the combustion process is mimicked here by an equivalent amount of energy addition at a constant pressure and constant Cp. So, here also we are assuming that the amount of heat that is added to this working fluid in the primary circuit is at constant pressure and Cp, essentially because in a combustion process, as I said you that Cp of the gas will change in the combustion chamber. So, it is advisable to consider the average value of Cp and gamma. for of course in the Cp in the combustion chamber, again Cp and gamma in the compression and inside the compressor and turbine. So, here also the process is represented by a constant pressure heat rejection process, and that is shown here 4:1. Now, if we try to draw the TS diagram, so these two processes are basically this is P2 equal to P3 and it is P4 equal to P1, because P4 equal to P1 because this process is at a constant pressure, you can see P4 equal to P1 equal to this. So, now this is the process 1 to 2 S. So, this is isentropic compression 1 to 2 S, 1 to 2 PV to the power gamma equal to constant. So, here PV to the power gamma equal to constant, here also, right, and this is P equal to constant, here P equal to constant, right. Now, so this is isentropic process, and also again there will be isentropic expansion. So, this is 3 and this is 4s, right. So, if we try to calculate or if we try to represent the compression process by an isentropic reversible adiabatic compression and reversible adiabatic expansion of the working fluid inside the turbine, then we can represent these two processes by these 1 to 2s and then 3 to 4s, these two lines at constant entropy. Now, question is, as I said that these two processes certainly will deviate from the reversible adiabatic process and processes, rather some degree of irreversibility will be there. And if we try to then represent the actual process, then actual process should be like this. So, this is 2. Similarly, entropy, it can be shown by using first TDS or second TDS equation. I am sorry, it can be shown by using or by making use of the second TDS equation, that entropy in the expansion process. So, basically if we need to if we consider the expansion process from 3 to 4, then in the direction of flow or forward flow direction, entropy will increase and the actual process would be like this. So, this is 4. So, now 1, 2, 3, 4, this is the actual process. So, I am writing 1, 2, 3, 4 actual cycle, Now, accounting for the losses due to irreversibility, we can define two important or efficiencies. One is isentropic efficiency of the compressor and isentropic efficiency of the turbine. Now, what is this? So, if I write isentropic efficiencies. So, for the compressor, eta compressor isentropic equal to, see, in a compressor is basically not a work producing device, it is a device which consume work. So, this is a work absorbing device. So, if we try to define what would be the definition of this isentropic efficiency of the compressor. So, actual work needed to be supplied to the compressor should be greater than the isentropic work needed to run the compressor following isentropic process. So, that means work input, needed following isentropic process between P1 and P2, that is two pressure limits, to the actual work input needed for the same pressure limit. That means Cp into, that means the work input needed to run the compressor following the isentropic process between two pressure limits, that is P1 and P2. We can see that P1 and P2, these two are the pressure limits, and actual work input. So, this is basically T2s minus T1 divided by Cp into T2 minus T1. You can understand, certainly the actual work needed to be supplied to the compressor should be higher than the work needed following the isentropic expansion. Hence, isentropic efficiency of the compressor will certainly be less than the predicted value using the isentropic process. So, this is basically the isentropic efficiency of the compressor. Similarly, isentropic efficiency for the turbine you can understand easily. Turbine is basically work producing device. Turbine is a work producing device. So, here what would be the definition? Now, in a turbine we are getting work output. So, actual work output should be less than the predicted one following the isentropic expansion. So, we can write here that actual work output between P3 and P4 to the work output following the isentropic expansion between P1, P3 and P4. So, this is essentially Cp into T3 minus T4 divided by Cp into T3 minus T4s. So, this this is the mathematical expression of the isentropic expansion of the turbine. So, we could write the isentropic expansion, isentropic efficiency of both compressor and turbine. Now, let us quickly take an effort to derive the cycle efficiency. We had seen that we can have the mathematical quantification of the cycle efficiency. We also can quantify the cycle efficiency knowing the efficiency of all units like compressor, then certainly the combustion efficiency, and then the turbine efficiency. If you try to recall, in the context of a steam power cycle, we could establish that the efficiency of a steam power cycle, overall efficiency, can be written like the efficiency of the boiler multiplied with the efficiency of the turbine, then multiplied with the efficiency of the condenser, and then with the pump. So, basically if we can figure out the efficiency of all these components, and then the overall efficiency will be multiplication of these efficiencies. So, now let us try to have, as I said you that the Breton cycle is basically the air standard cycle for the gas turbine units. In other word, I can tell you that when you are trying to quantify the when you try to mathematically quantify the thermal performance, thermal efficiency, then we need to compare all the processes by using an air standard cycle. So, and that cycle is for this particular gas turbine unit, for this particular power producing unit, to be precise, gas turbine unit is the Breton cycle. So, if we just again redraw the TS diagram, and then if we, so this is 1, 2 and 3 and 4. So, again we shall try to quantify the efficiency, assuming that the compression process and expansion process, these two processes are reversible adiabatic. So, here this is basically W turbine or W out, this is basically W C, this is basically Q in and this is Q out. So, what is the efficiency? Thermal efficiency, or I should say efficiency of the cycle is W net divided by Q in, that we have studied in our basic thermodynamic course. So, what is W net? If we go back to the either closed cycle unit or if even for the open cycle unit, this is W T minus W C, that is the turbine work which is produced minus the work, the part of that work that is fed to the compressor for its operation. So, if we write here, that is W net equal to W turbine minus W compressor. So, what is W turbine? You can see from this TS diagram that Cp into T3 minus T4. We are assuming that Cp, as I said you that in real application it would be correct if we can consider the average value of Cp and gamma, because this process 3 to 4 and 1 to 2, these two processes mathematically represented by the relation Pv to the power gamma equal to constant, and this gamma should be taken average, because average gamma, otherwise because in the expansion and compression process gamma will change. Particularly in the compression process, if I go here, compression process Cp and gamma will certainly be changed. Why? In this in the real application, what is done, that if we go back to the open cycle gas turbine unit, we are supplying fuel. That fuel is supplied and combustion reaction has taken place. So, and it is because of this particular factor gamma and Cp will change, and so it is advisable to consider average value of Cp and gamma when we will be calculating the properties at the exit of the turbine using air standard equation, that is Pv to the power gamma equal to constant. So, here Cp into T3 minus T4 minus compressor work is Cp into T2 minus T1. As I said that here we are not going to consider the actual processes, rather we are going to consider the isentropic processes for the compression and turbine processes. So, this is W net, and what about Q in? Q in equal to Cp into T3 minus T2. So, that is the heat addition. So, if we now write the cycle efficiency, then we can write eta cycle equal to Cp into T3 minus T4 minus Cp into T2 minus T1 divided by Cp into T3 minus T2. We can write one step further, we can write that T3 minus T2 minus T4 minus T1 divided by T3 minus T2, and that is basically 1 minus T4 minus T1 divided by T3 minus T2. So, this is the mathematical expression of the cycle efficiency of the gas turbine unit. So, now we can again rewrite this. So, if we try to recall the process 1 to 2, few minutes back I have discussed that this is essentially a reversible adiabatic compression, and that is represented by this process P v power gamma equal to constant, right. So, that means we can write what would be the rise in temperature due to the compression process. If you try to recall, I have mentioned that after compression certainly pressure of the air will be higher, but temperature also will increase. So, T2 by T1 equal to P2 by P1 power gamma by gamma minus 1. So, that is the sorry, I did mistake, it should be gamma minus 1 upon gamma, because this is P2 by P1. Okay. So, this should be gamma minus 1 upon gamma, gamma minus 1 upon gamma. What is P2? P2 equal to P3 and P4 equal to P1. So, we can write P2 by P1 equal to P3 by P4. So, that we can write equal to P3 by P4, and this is again power gamma minus 1 upon gamma, and hence this should be T3 by T4. Therefore, we can write T4 by T1 equal to T3 by T2. Therefore, we can write T4 minus T1. If we just subtract 1 from both sides, then T4 minus T1 divided by T3 minus T2, that should be equal to T1 by T2, right, simply T1 by T2. So, this is what we had obtained using air standard equation by representing the compression process like this, and then because P4 equal to P1 and P3 equal to P2, and then we could write the ratio of T4 minus T1 to T3 minus T2 like T1 by T2. So, what we can write again, then cycle efficiency equal to 1 minus T1 by T2. So, what is 1 minus T1 by T2, or 1 minus if T1 by T2, just you try to understand if T1 by T2, then we can again write 1 minus 1 upon T2 by T1. So, that equal to 1 minus 1 upon what is T2 by T1? T2 by T1, that is P2 by P1 power gamma minus 1 upon gamma. So, that is P2 by P1 power gamma minus 1 upon gamma. What is P2 by P1? So, you can understand P2, that is the pressure of the working fluid at the exit of the compressor, and P1 is the pressure of the working fluid at the inlet of the compressor. So, this P2 by P1, that is called pressure ratio, and is represented by Rp. So, essentially rise in pressure of the working fluid due to the compression process, and that is Rp. So, we can write it as cycle equal to 1 upon 1 power 1 minus 1 upon Rp power gamma minus 1 upon gamma. What you can understand from this expression is that if we somehow increase the pressure ratio, that means if we can compress the air, to the higher extent, then efficiency of the cycle will be more. So, that means higher the compression ratio, higher will be the efficiency of the gas turbine unit or cycle efficiency. So, this is basically the expression. So, if when RP is higher, eta cycle will increase. So, now question is, we also can write this mathematical efficiency like this. So, what is this? Eta cycle equal to 1 minus T1 by T2. So, what is T1 by T2? Again using this air standard equation we can write 1 minus V2 by V1 power gamma minus 1, right. So, this is 1 minus V2 by V1 power gamma minus 1. So, we can write again this 1 minus 1 upon V1 power V2 V1 by V2 power gamma minus 1. What is V1 by V2? So, V1 by V2, again if we go back to the PV diagram. So, basically here this is the V1, and at the end of the compression process volume has reduced, and it is because of this reduction in volume we could increase the pressure from P1 to P2, and the ratio of V1 by V2, if you try to recall, we have discussed in the context of Otto cycle, is known as the compression ratio. That means, we could compress the air or any other working substance, and it is because of this compression we could increase the temperature of the working fluid, pressure of the working fluid. Also temperature will increase, not as I said you that pressure increase is more than the rise in or increase in temperature. So, here we can write that V1 by V2 is equal to compression ratio or RK or RC. So, this is known as compression ratio. So, we also can write eta cycle equal to 1 minus 1 upon RC power gamma minus 1, right. So, for the same compression ratio, if the compression ratio is same, efficiency of the Breton cycle. So, basically this is the Breton cycle efficiency. Efficiency of the Breton cycle will be equal to the efficiency of the Otto cycle. So, for the same compression ratio. So, to summarize today's discussion, we have discussed about the gas turbine unit, we have classified the gas turbine units, and then we have discussed about the operation of both open cycle and gas turbine units. Then we could define the isentropic efficiency of both compressor and turbines, and finally we could establish the cycle efficiency, and then we have expressed the cycle efficiency both in terms of pressure ratio and the compression ratio. So, with this I stop here today, and we shall continue our discussion in the next class. Thank you.